Welcome to Limits, Lesson 5, Continuity on an Interval, where we are going to take it to the limit one more time. Wow, how embarrassing. I didn't think the mic was going to pick up my voice that much. Anyway, yeah, I know. Don't quit my day job, I know. Anyway, that was brought to you by the Eagles. I've been waiting to do that in a calc class for years, and I just never had an opportunity to do it. Hey, this opens it up. All right, before we talk about continuity on interval, I would like to talk about one-sided limits one more time. So let's go ahead and move on. All right. What is the limit as x approaches 0 from the right of the nth root of x? Okay, what did we learn to do? We learned to replace. So let's go ahead and put a 0 in there. How about if I have a pen? Yes, I have a pen. So what is the nth root of 0? Okay, that could be the cube root, could be the square root, could be the fourth root, could be the 10th root. That's going to equal 0. Okay? Now let's go ahead and do the same thing. The limit as x approaches 0 from the left, replace with a 0, and the nth root is, does not exist for n equaling 2k, and 0 for n equaling 2k plus 1. What are you talking about, Manning? What is this 2k and 2k plus 1? Alright, that makes this right here makes n an even number. So since we're approaching 0 from the left, we're talking about a negative number. And if we try to take the square root of a negative number, or the fourth root of a negative number, or the sixth root of a negative number, it's just not going to work. However, we can take the cube root of a negative number, or the fifth root, or the seventh root of a negative number. That would indeed be 0. So, depending on which way you go, the limit may exist or may not exist. Let's go ahead and look at another one. What's the limit as we approach negative 2 from the right? Which means we are talking about like negative 1.99 or negative 1.8 or something like that. So when we replace that in there with a 2, it's going to be the square root of 4 minus 2 squared. But it's going to be a little bit less than 2 every time, so we don't have to worry about it going over 4. So the limit would be 0. However, if we approach negative 2 from the left, okay, we're talking like negative 2.1 or negative 2.01 when we replace this in here. It's always going to be a little bit more than 2. Well, actually, a little bit less than 2. Where did that 0 come from? I have no idea. Oh, wow! I just put the slate onto the keyboard. Sorry about that. So anyway, when you put that negative 2 in there, it's going to be a little bit more. This is going to end up being, when you square it, a little bit more than 4. This limit does not exist, because you're going to end up with a negative inside the square root, and that's always a bad idea. And the same thing with these two functions, or these two limits. Okay, when you approach 2 from the left, okay, this time we're approaching from the left 1.99 to 1.9999. Okay, it's always going to be a little bit less than 2 put in for x, which means this is going to be approaching 4 because we're squaring it, so that would be 0. And here, when you're approaching 2 from the right, it's going to be 2.1. Or 2.01, you get it, 2.01. So this squared is always going to be a little bit more than 4, which means it's going to be 4 minus something that's a little bit more than 4, that limit will not exist because it will give us a negative inside that radical, which is always a bad thing. Alright, I would now like to introduce to you the greatest integer function. Wow, sorry about that. I'm kind of loud tonight. Alright, let's go ahead and move on. Right there. F of x equals the greatest integer function. That's a very special notation there. And what that says is as you move along on your x's, what is the greatest integer that you come across? Let's start at 0. How about at 0.5? What's the greatest integer you've come across? 0. How about at 0.75? Still, the greatest integer you've come across is 0. Until you pop up to 1, it jumps up here, and it's defined there at 1. And that would be the greatest integer you've come across as you move along. And it just keeps on hop-stepping all the way up. This is truly the sickest function that there is. Alright, here we are. Again. That was a good half an hour wait. Got interrupted. Alright. What is the limit of f of x as x approaches 0 from the left? So you're approaching 0 from the left right here. What is the limit? Come on. You can guess. You can figure it out. That is correct. The limit would be -1. What would be the limit of f of x as you approach 0 from the right? As you approach 0 from the right, the limit is 0. This is truly not a fun function. Okay? You want to make things even worse? Sure, we can make it worse. How about if we make this function right here? Okay, isn't that fun? G of x equals the greatest integer function plus 3. Yeah, I'll let you try to graph that one. Good luck. And I'm not even going to show the answer because you know how long it took me to move stuff around to graph that greatest integer function? Way too much. But let's go ahead and try to figure out this right here. What's the limit of g of x as x approaches 2 from the left? Okay, so it's always going to be a little bit less than 2, because we're coming from there. So it would be a 1. Limit would be 4. How about the limit of g of x as we're approaching 2 from the right side? Okay, as you're approaching 2 from the right side, it's always going to be a little bit more than 2, always a little bit more than 2, but the greatest integer would be 2, so the limit would be 5. Yeah, I know, it's really messed up. Alright, I think we're now ready to talk about continuity. Now let's go back and look at f of x just a little bit, okay? On what intervals is this function continuous? Yeah, there's a bunch of intervals where it's continuous. It is solid. There's no breaks in it. But there's a bunch of intervals as it goes up the line here. All right, let's go ahead and look at the definition of continuity on an interval. All right, I'll go ahead and let you read this and write it down. So I'm going to pause just for a second. Be right back. All right, did you get that down? So this right here would be the greatest integer function kind of thing going on, because it is equal to the left limit, and as you get closer and closer, like this, if this was 0 and this was 1, it would include 0 as the greatest integer, but it would not include 1, because as it got close to 1, and it gets to 1, then it would be on this interval, just like that. That's how the greatest integer function works. It works like that. That's kind of what the greatest integer function's going on there. Alright, let's see if I've got examples for you. Well, no, I got properties of continuity. If b is a real number and f and g are continuous at a point x equals c, then the following functions are continuous at x equals c. B times that function f, b times that function g. If I add those two functions f and g together, or take the difference of them if I multiply them together, if I take the quotient of them, they will be continuous at c if, of course, g of c is not equal to 0, because then you would be dividing by 0 on that. Those are the properties of continuity. And yes, I know continuity is a pentasyllabic word. Alright. These functions are continuous at all points of their domain. All the polynomial functions like f of x equals x cubed plus 3x squared plus 3x plus 1. Polynomial functions. Rational functions like x minus 3 over x plus 3. They're continuous at all points of their domain. The domain for that rational function, of course, is negative infinity to negative 3 unioned with negative 3 to infinity. That's the domain. So it's continuous on its domain. Obviously, it's not continuous at x equals negative 3. Probably a non-removable asymptotic discontinuity. Radical functions like 4 minus x squared, square root of that. The domain of that is negative 2 to 2. So it is continuous on its domain. And all the trigonometric functions. Those are continuous everywhere along their functions. Tangent, cotangent, secant, and cosecant will of course have some vertical asymptotes depending on which graph you're talking about. But where it's defined, it will be continuous. And I think that's about all I have to say on that. Anyway, have a great evening. See you tomorrow in class. This does conclude Limits, Lesson 5, Continuity on an Interval.